Of week 2. So Max will finish telling us SPT phases of bosons.
All right. Thanks for sticking around till the bitter end of week 2. Remember last time we started talking about invertible phases with a global symmetry, and we introduced the notion of symmetry-protected topological phases, and we said that for bosons there is this construction going back to Dijkgraaf and Witten that's now known as the cohomology construction of these SPT phases of bosons. The way that works is that it takes as an input an algebraic object which is an element of this d-dimensional cohomology group where d is the space-time dimension. And from it you can build a partition function on any manifold by looking at the d simplices on the manifold and just kind of taking products of cocycles on every d simplex. Yes. Maybe it's a d equal 3. We have tetrahedra then. Doesn't really matter. Okay, so remember there are group elements sitting on every vertex here, G naught, G1, G2, something like this. Okay, and remember what we saw was that the partition function of these phases on any closed manifold was equal to 1, which is not very interesting, but we reasoned that away as well. It actually had to be that way. Okay, so now what is the goal for today? The goal for today is to see, first of all, kind of main goal is to distinguish these phases. Right now it doesn't look like they're different phases, so the goal is to distinguish them, and we will talk about it in several ways. We'll look at what is happening on the boundary, and we will also talk about what happens if you couple the system to a background gauge field for the group G, and we'll see that will give a way to distinguish these phases. Okay, so let's see. So first question that I'd like to ask, remember we call this product, we call this the action, which depends on the group element sitting on the vertices, and we saw that that this action is actually equal to 1 as long as the manifold is closed. So what if the manifold is open? What if the manifold has a boundary? So suppose I have some manifold with a boundary. How do I draw it? Let me draw it. Suppose it's a two-dimensional manifold with a boundary, so there are kind of triangles going into here. D equal 2. And there are group elements sitting away from on vertices away from the boundary and on vertices on the boundary. So there's like G bulk and G boundary. And my claim is that e to the minus s of G, the action, actually only depends on the group elements on the boundary. Yeah, only depends on the boundary and on the group elements on the boundary. And the way to see that is that if I have if I have a different manifold, so let's call this M, and this is M prime, but with the same boundary, with the same G boundary, but with a different G prime bulk. Well, in fact, the way the bulk is triangulated and the topology of the bulk would be completely different. My claim is that the actions are the same. Right, so here G prime boundary is equal to G boundary. And the way to see that is simply to take this manifold M, take the manifold M prime with an opposite orientation. So consider M union M prime with the opposite orientation, and yeah, so just glue them together. You'll get, so this will be M, this will be M prime bar, and because the boundaries are the same and the configurations of group elements on the boundary are the same, then this glues nicely, right? So we get a closed manifold, and we know that on a closed manifold the partition function or the action is equal to 1. So that means that, well, if you think about this orientation reversal, that takes the complex conjugate, so that means this is true. Okay, so when we have a boundary, the action just depends on what's happening on the boundary. That doesn't depend on what's happening in the bulk. So this will be very useful to us. So let's use this fact in order to calculate the wave function, the ground state wave function of the system. Ground state wave function. So ground state wave function will have to be on some manifold which is one low dimension, right? Just a spatial manifold. Let's suppose closed spatial manifold. All right. Remember, Tom taught us that if you look at a cylinder, y d minus 1 cross interval, where so this is our y d minus 1, maybe a circle, and we have time going this way. Then remember, if I calculate the partition function on this cylinder with fixed boundary conditions, maybe I have some g prime sitting here, right? So this collectively denote the group elements on the triangulation of the manifold yd minus 1, and yeah, on this boundary and this boundary, then this is just the matrix element. G prime. Maybe I should put e to the minus ht, where t is the length of this G. And using the spectral decomposition, when t goes to infinity, assuming I have a gap phase, this will just be G prime 0 times 0 G, where 0 is the ground state. So this is the ground state wave function, complex conjugated at G prime times the ground state wave function at G.
Did you drop the exponential?
Yes. Thank you. Now clearly we have a single ground state, because if you take trace, well, if we close up this cylinder we get a torus, and we know that partition function on on any closed manifold is 1. So that means, if you had more than a single ground state, you would have like a number here. So since the absolute value since the absolute value of the partition function is 1, and in fact the partition function is 1, you know that you have a unique ground state. The energy must be 0, but that doesn't really matter. And we can read off these wave functions in the following way. So this path integral should give us this product, but actually we can get each individual term, and there is actually something very nice we can do. Right? Remember, the action only depends on the values of the G elements on the boundary. So we can replace this manifold by a manifold like this. Right, so this, we have G here, G prime, sorry, and G. So that it would mean that this partition function, where this is kind of capped off, would evaluate psi 0 of G prime star, and this one would evaluate psi 0 of G, G here. And there are triangles going into the bulk, so that's okay. I'm not keeping track of the orientation, but if I kept track of the orientation, then I would figure out the stars and stuff. Okay, so that's nice. But actually, each one of these partition functions we can evaluate in a very simple way. We can just have one single vertex in the bulk. Right? We can suppose. Right? Remember, it doesn't matter what I have in the bulk, so might as well just have a single vertex there. So maybe if my boundary is this one-dimensional circle, then I simply have a single point G star in the bulk here, and I just triangulate like this with let's draw this one. I don't want to deal with a star, since I'm not keeping track of it anyway. Right? So you'll have G star here, and etc. So I build this cap just in this way by connecting everything to a single point with an element G star sitting at that point. Okay, so that means that the wave function, let me write it out now, psi of G, right, where G are the group elements on the boundary, will just be a product over the simplices, d-1 simplices on this boundary, new G of the simplex, and then, right, so in this case, for instance, the simplices are one-dimensional, so I have like G0, G1, and at the end I have G star. So I take product over the simplices in the d-1 dimensional manifold, and I kind of complete them to a D simplex this way, and I take nu. Questions? So now, right. So in principle, I should be doing this whole story of taking sum over GV in the bulk, right? But I have just one vertex in the bulk, and the action shouldn't be dependent on what I have in the bulk there. So actually, I just get that. it seems like this should depend on what G star is, but turns out that you don't, that it doesn't. And the reason is that this is a closed, that YD minus 1 is a closed manifold. All right. It's okay? So here we're thinking about so this is the ground state wave function of the system. So we're kind of thinking about a temporal slice, if you wish. What if you think about a spatial slice? So what if you think about a real physical boundary of the system? Can we figure out what's going on there? Well, we can do something very simple. Sorry, not very simple, very similar. Spatial boundary. So spatial. Let's say, just to be more interesting, let's say I have a two-dimensional, let's say my bulk has two spatial dimensions. So maybe my bulk manifold is a disk. Doesn't really matter, but so this is a picture when D is equal to 2 plus 1. So here is the boundary of a disk is a circle, and here is time is going this way. Okay, so we have our action for our system. So we can evaluate the partition function here, and well, there are some group elements G node G1, G2, G3 sitting on the boundary, right? And something like this. So let's do the following. Let's try to figure out, can we build an effective action, or more precisely an effective Hamiltonian for the boundary, right? So I can kind of think about it in the following way. So first of all, no matter how many points I have on the boundary here, remember I can just, to calculate the full partition function, I can just pick one point in the bulk. So let me put an element G star in the bulk here, and just connect everything over to that element G star. So that will produce my three simplices. I'll draw them. I'll try to draw them in a second. But what I'll be interested in is the following matrix element. Let me think about some G. Let me think of this as kind of like a single time slice from here up to here. And let me think about computing the matrix. Let's say that this is delta tau. And let me think about computing the matrix element of H delta tau between the values of G here on the boundary and the values of G here on the boundary. And G star I'll redraw in a second. So they're supposed to go vertically. Let's see. G1 prime, G0 prime, G2 prime, G3 prime. Okay? So I want to compute this matrix element, and effectively this should give me the boundary Hamiltonian if I am able to compute this. Further, and we can kind of integrate the entire bulk out and just replace it by this single vertex G star sitting in the bulk. So, and then when I do this, I might need more intermediate vertices on the boundary. That will not matter for now. Let me just kind of draw it like this. I triangulate the boundary like this, and then each one of these I can connect to the single bulk I will not attempt to draw that. But anyway, so what does that give me? That gives me 1 over evaluating that partition function. So if I have some intermediate vertices here in the middle, then okay, I do 1 over g, and then I sum over whatever, if I need some additional points on the boundary, I sum over those points. These are not the points in the bulk. And I take the product over the boundary simplices. So in this case, they will just be these triangles. And I take nu of g on the boundary simplices. So in this case, 2 simplices. -1. And the last point is always the bulk point to which I connect everything to get my d simplices. And orientation. Okay? So this is what the matrix element looks like. Now you can ask, well, is this invariant under the G action? Is this symmetric? Right? I can look at compared to G naught, G prime. So this is really a collection of all the G's on the boundary. G naught, G prime, G naught, G. Okay, I get the same thing, except here I get G naught instead of G. Nu G naught, G delta D minus 1, G star X. Right, so I'm just thinking about acting with group element G naught on this matrix element, and I'm trying to check if my boundary Hamiltonian is symmetric or not. Well, it doesn't look symmetric, right? Because okay, so this is a homogeneous cocycle, so I can move this G naught onto here. I can replace this by nu G delta D minus 1 G naught inverse G star S. But there is this G naught inverse G star, which is different from G star in general. So each one of these nus is actually different. So so the matrix element doesn't look like it's invariant, and it's not. But what you can show is that if you look at these cocycles and you change the last element, just as we are doing here, then it's the same as the original expression up to a coboundary where this mu is a d minus 2-dimensional Okay, so they're just different by a coboundary, and as a result, these two matrix elements are related by the following factors. Let me write it. in the following way. G naught G prime T G naught G is equal to G naught e to the minus H delta tau G times product over delta d minus 2 belonging just to this. Let me call just the spatial piece of the boundary. Let me call that this x d minus 2. So boundary as a space-time is d minus 1 dimensional. The spatial part of the boundary is just d minus 2 dimensional, right? Like a circle here of mu of g prime delta d minus 2 over mu of g prime delta of g delta d minus 2 times orientation. Now there might be various factors of minus 1 to the d that I'm not going to try to keep track of. Yes?
Could you explain that middle formula one more time?
This one?
Yes, is d minus 2 cochain mu is equal to d cochain?
Right. So mu will depend on g star and on g naught, and it depends through this. Right. So mu is a d minus 2 cochain. It depends on d minus 2 group elements. So these are the d minus 2 group elements, and then this just come along for the right, and then this formula is true, because you can check it's true because nu is a is closed cocycle, right? So then, we're kind of taking this d mu and we are integrating it over to the boundary. So I'm not going to go through the technical details, but that's what you get.
There's a question over here.
Right.
So we have two different G naughts, right? There's the G naught that's the configuration on the lower thing, and then there's the G naught that you're using to see if this is invariant. Is that true?
No.
Okay.
So like this single point. Oh shoot. Let's just start with 1. Yeah. Sorry, that G naught is some other group element in G that we are trying to act with.
So in this cochain formula, the G naught at the beginning is not necessarily the G naught that's inversed at the end.
Yeah. Let's say H my apologies. Maybe that was the reason for the confusion. H inverse. Yes. Okay, I think this is pretty good now. Okay, so you see that this acting with H gives us some factor that can be written as a product of something over the final state and something over the initial state. So that means that even though our boundary Hamiltonian H is not invariant, so this should be thought as an effective boundary Hamiltonian now, right? It just acts on the boundary degrees of freedom. It's not invariant under just shifting all the g's to h times g, but it is invariant if we multiply by this additional factor. So the following is going to be a symmetry. U of H on G. So everything here is on the boundary. So product over delta D minus 2 in X D minus 2 nu of G D minus 2 G star H inverse G star So we do rotate all our group elements on the boundary globally by H, but we also multiply by this factor. And by that formula, this U of H is going to commute with effective boundary Hamiltonian. So, okay, so that's interesting. So the boundary is just boundary Hilbert space is just an ordinary Hilbert space, nothing weird about it. The effective Hamiltonian that we kind of are deriving here is also perfectly nice local Hamiltonian, nothing wrong with it. It's just that the symmetry, effectively the symmetry acts on the boundary in a weird way. So let's investigate this weirdness. So let's say we are in 1 plus 1 dimensions, right? So the boundary is just 0 plus 1 dimensional then. So the boundary just has a single group element sitting on it. 1 plus 1, right? So we have and here is our boundaries, our spatial boundaries. So we have just on each boundary point, we have just a single, the Hilbert space is just composed of the group elements. And now U of H on, so there is some G sitting here, on G is going to give us what? It's going to give us nu of, well, the simplex now has just a single point, G star, G inverse, H inverse G star, okay, so this is the effective symmetry action on the boundary, and you can check that that this is precisely a projective symmetry action. U of H, U of K is going to be equal to W K inverse H inverse U of HK, where W is the inhomogeneous cocycle. And this turns out to be the same as W of HK. Maybe with an inverse. Yes, with an inverse. Okay, so we see that we're actually getting exactly the, remember last lecture we kind of guessed that for 1 plus 1 dimensional SPT, on the boundary we're going to get the symmetry acting projectively, and these models kind of realize that precisely. Okay, so maybe this is not so interesting. What about if we go to 1 higher dimensions? Let's have an example in G2 plus 1 dimensions. Okay, G equal 2 plus 1. And let me, so the boundary is just one spatial dimension. So let me be very, so first of all, okay, well, how does the symmetry action look like? It looks like this, U of H on G, right? So now my boundary, the spatially is just maybe a circle with G1, G2, G3, okay, going all the way. And this is going to be product. I just read off that top formula. The simplices are now one-dimensional, so now this is nu of Gi plus 1 G star H inverse G star Hg. Okay, so this is kind of interesting, right? So I'm first rotating all the group elements by H, but I'm also multiplying by this thing, and this thing is kind of a product over all the bonds, and the product depends on the G values on each of the bonds. So it's some weird thing. Well, let's just have a very explicit example of this. Let's pick the symmetry group to be Z2. Okay, so you can ask what are the cocycles for Z2 in 2 plus 1 dimensions. Turns out that this this group is just Z2, and the non-trivial cocycle is the following. Let me write it as an inhomogeneous cocycle. So first of all, right, so group being Z2, let me add it, write it in an additive way as 0, 1, right? So I'll think of the symmetry operation as addition, and the inhomogeneous cocycle, 3 cocycle, is this. Right? So it's trivial unless G, H, and K are all equal to 1. Okay. So let's just compute this this action, this group, this symmetry action in this case. So on each side I have elements of the group sitting on the right. So so on each side I have either 0 or 1. So it's like a spin 1/2 on each side. So I have a circle, spin 1/2 on each side of the circle. To be specific, let's do the following. Let's choose G star equal to 0, right? And we are trying to compute the symmetry action for the group element 1. So remember, nu of G, H, K, L is related to omega in this way. Gi inverse H, H inverse K, K inverse L. Well, except now I should use the addition, right? So no longer using the multiplicative, right? So then using the expression for omega, this becomes product over I minus 1 of Gi plus Gi plus 1 times G star. Okay, so H is now 1, right? That's the non-trivial. This is H. This is the generator of the Z2. And then here I have okay, times Gi plus 1 times So this is the action on some G. It's going to be this times 1. And then here just all G's get shifted by 1. Okay, so some weird factor like that. So you can ask physically. Okay, so I have a bunch of zeros and ones, so I can also say like 0 is up and 1 is down. And I flip all the, right, so 0, 1. I flip all the spins, and I multiply by this phase factor. You can ask, what is this phase factor? You can convince yourself that this is -1 to the number of domain walls on the circle over 2 times. Right? So whenever I have a up next to a down, that's a domain wall. On a circle, the number of domain walls is even. So this is going to be an integer. So -1, so I either get a +1 or -1. All right. So now a couple of comments about this. So first of all, this symmetry operation is a finite depth local unitary. I mean, it maps. Well, first of all, it maps local operators to local operators. Second, I can decompose it into like commuting local operators which are separated. So there's nothing wrong with this symmetry action. The only thing is that I cannot write U as a, there is no way to decompose U as a product over sites, or maybe like I can group sites together of something that only acts on those sites and satisfies the group law. So U is not on site. Remember we had the definition of on-site symmetry in the last lecture. We said an on-site symmetry is one that factors like this, satisfying the group law on each site. And the site doesn't have to be just a single site. I can group things together. So maybe you'll tell me, okay, you're just not smart enough. Maybe there is some way to write this -1 to the number of domain walls over 2 in this way. There's maybe some way to factor it like this. Turns out the answer is no. There is actually an algebraic abstraction to converting this into a product like this. And there is a very nice theory of such abstractions that was developed by Dominic Els and Chetan Nayak. And the abstraction, what do you guess the abstraction is? The abstraction is just this cocycle, this 3 cocycle. Abstraction to on-siteness H3 GU1, which is precisely the 3 cocycle that goes as an input into the phase. So this is Nayak Elze 2014. And in fact, for any symmetry, for any finite depth local unitary in one spatial dimension, you can compute this abstraction. It will always be a cocycle. So that's kind of a nice. You can, if someone tells you the action of the symmetry on the boundary, you can read off the bulk SPT phase. So we'll see that the boundaries of these SPT phases, they're anomalous. And usually you think about anomalies in a kind of a, so people say different things. You usually think about it in the continuum. Well, here's a way to think about an anomaly on the lattice. And at least for this class of phases, the anomalous boundary has an ordinary Hilbert space, has a symmetry action which is a finite depth local unitary, but one which is a non-on-site, and the non-on-siteness is characterized by the cocycle. How does that connect with our usual understanding of anomalies? Well, remember, anomalous symmetries are global symmetries that cannot be consistently coupled to a gauge field. Well, not clear how to, because it doesn't decompose in this form, it's not clear how to couple it to a gauge field. So everything is kind of consistent, but this is a slightly different perspective. All right. So let's see how we're doing on time. Have half an hour. Okay, so I told you something about the boundary, but we can say, okay, is there a way to? So first of all, this gives us a way to distinguish the phases, right? We just look at the boundary, we read off the non-on-site symmetry action on the boundary, we extract the cocycle from it, and okay, that's a way to distinguish the phases. But is there a way to do it just from the bulk? And the answer is yes. And the way to do that is you need to couple your system to a background gauge field. So let's talk about that. Can maybe start. So let's very quickly review gauge fields on manifolds. You probably seen that if you have a manifold, well, a manifold is a collection of patches that can overlap, right? If we let's call them patch 1, 2, 3 here. Suppose our gauge group is G. Then we define the G bundle over the manifold as a collection of functions which are valued in the intersections of the that are defined on the intersections of these patches and take values in G, and they have to be smooth functions. Well, if G is discrete, then because these intersections we can choose as connected, then on each intersection U must just be a constant. If G is discrete, Uij of x is just some Uij, some constant. Okay, if we have some matter fields which are charged under G, then as you go from one patch to the other, so the matter fields are defined on each patch, and as you go from one patch to the other, you need this transition function. So these are known as transition functions. Okay. Well, in general, you would use the appropriate representation for whatever representation of phi is, but let me not worry about that. But for this thing to be consistent, we need some consistency condition on the use on triple intersection of patches, right? Because I can, on this triple intersection, I can go like from 1 to 2 to 3 like this, or I can go from 1 to 3 directly. So that gives me a consistency condition. Satisfy U13 is equal to U12 times U23 on patch intersections. Okay. Of course, on each patch I can perform a gauge transformation. Gauge transforms on each patch. And then the transition functions will need to also transform So these transition functions, you define the G bundle over our manifold. We can say that the matter fields are sections of that bundle. Okay, so transition functions modulo these transformations, of course. All right. So for a discrete gauge field, everything is kind of we can kind of replace all of these by our simplicial structures. Kind of morally, just put a vertex in the center of each patch, and then start connecting the vertices by one simplices, by edges. So on each edge, then you have a group element sitting. So use G discrete. Use live on edges of our triangulation, on edges of our triangulation. And they still, so for every, then this consistency condition is that on every 2 simplex, we have U01, U12 is going to be equal to U02. So U02 okay. And the gauge transformations just take exactly the same form, except now no x dependence, and and this I and j are just site indices. Questions? Okay, so now we had our partition function of our model with a global symmetry G. Let's try to promote that global symmetry to a local symmetry. So let's couple it to a background G gauge field. So initially we had Z is 1. Well, let me not write that one factor. It's not very important. So sum over G, product of a delta D in the manifold, new D, G naught G1 G D on each simplex, S of delta. Okay. So we had a global symmetry, right? Gi going to HGI. Let's try to gauge that. So now Gi is going to, so let's gauge. I can have a gauge transformation on every side, and then I'll have to have gauge fields on the links. Right, so I have G's. I still have G's sitting on the side of on the sides of my complex, but now I have U's sitting on the links, satisfying the consistency condition there, and okay, they transform in this way. So I have to kind of modify this action so that it's invariant under these transformations, and there is a nice way of doing that. So here the Z just depended on the manifold. Now here Z is going to depend on the manifold and the background gauge field U. And the way we modify things is that, well, we take our, let's look at one of the simplices. Okay, so the first point we still put G naught, and then here we say U naught 1, G1. So we kind of take this G on this vertex and we use our gauge field to pull it to vertex 0. It's kind of like a Wilson line. Well, in fact, it is a Wilson line. And then for G2, we do U01, U12, G2, etc. And then for the last vertex, we'll have U01, U12, GD. I could have written U02 here using our consistency condition, but I'm writing it in this weird way. All right. So let's see. So this is clearly gauge invariant. Tom?
So I'm a little bit confused. So you don't have an action for the U's themselves. Is the game that you are playing that you impose some particular pattern of U's on your system, or are the U's themselves going to be dynamical variables?
I can play either game, but so the question was whether I have the observation was that I don't have any explicit separate action for the U's, and I also don't have a sum of a U's here, and I have my partition function depending on U. So for now, I'm just going to think of U as a background gauge field that's going to be used as a probe of the system. And later, if we have time, we'll talk about what happens if I start summing over U's as well. Yes, that's the reason we wrote. That's essentially the reason that we have this weird U01, U12 that we chose to write it in this way. So the question was whether there is a slicker way of writing this in terms of inhomogeneous cocycles, and there is, and we'll have one in just a second. So, okay, so these products of U's transform in a nice way on the gauge transformations where you would just pick up a V0 everywhere here, and because this is a homogeneous cocycle, if I multiply all the elements by V0, I get the same thing. So this is gauge invariant by construction. Now let's, as was suggested, let's write this in terms of the inhomogeneous cocycle omega, or W, D. Okay. Omega D. So I need to do G naught inverse U01 G1, then G1 inverse U12 G2, and at the very end I'll have GD minus 1 inverse UD minus 1D GD. All right. So if I didn't have these G's around, what would this be? This would simply be the entries would just be the values of U on the ascending links of each triangulation, right? U01, U12, U23 if it's a tetrahedron, etc. And with the G's, what is it? Well, it's really just like I took my G's. It's just like I took my U's and I gauge transformed by G. I can think of U G I J is Gi inverse Uij Gj. This is U transformed, gauge transformed by G. So I can write this as sum over G, product of a delta D. Let me write it schematically like this. Now, a non-entirely trivial statement is that let's write down the following action. Let's write down e to the minus s of U is equal to product of a delta D omega D of U on that simplex to the s. My claim is that if my manifold M is closed, for M closed, this is gauge invariant. That is, these expressions, these products, don't depend on G. So then it's trivial to take the sum over G's, and yeah. How to see this? Well, the way to see this is the following. Let's think about some higher dimensional manifold where I put U's on every link, and let's suppose that in that higher dimensional manifold, or not necessarily manifold, just a simplicial complex, I have this condition obeyed on every triangle, on every two simplex. And my claim is that WD defines a D cocycle on that manifold in the simplicial sense. So let's think just on some manifold of dimension potentially larger than D. My claim is that the fact that U is flat, which is this condition, so flat. Let's call this flat. And second, that WD is a group cocycle implies that WD becomes a simplicial cocycle. on this manifold. Right? So WD is something which is defined on every D simplex via this expression, and I claim that it's closed in the simplicial sense. Why is that useful? Well, suppose I have some U, and I make a gauge transformation, and suppose I just make a gauge transformation on a single vertex. Right, so suppose this is vertex V, and here I make a gauge transformation with some group element G on that vertex. You can convince yourself that you can kind of close this off in such a way that, well, first of all, that on the kind of top layer of this, you'll get UG, the gauge transformed U, and such that on this kind of simplices going up vertically, you can assign values of U such that everything is flat. And that means that if I integrate my omega over the bottom of this, where my U is not gauge transformed, it's the same as integrating omega over the top of this, where my U is gauge transformed. And because omega is closed as a simplicial cochain, those two integrals are the same, so that proves gauge invariance. There is all of this is described in very nice detail in a paper by WWW, Wang, Wen, and Witten, in some order. Okay. So let's see. So that's nice. So it means that this is not going to depend on G. So then it means that I don't have to do any sums. I just take my omega D over every simplex, and I take the product, and that's going to be my partition function. So my partition function, so this works on a closed manifold. So for M closed, so the partition function on a closed manifold is now again a pure phase, but this phase depends on the background gauge field U on the manifold, and it's not always 1. In fact, if the cocycle is non-trivial, then it's not going to be 1. Another observation that follows is that this partition function is now a Bordism invariant. It's a Bordism invariant of manifolds with G gauge field defined on them. Bordism invariant of manifolds with G gauge fields. So suppose I have some manifold M1 with a G gauge field U1. Here is manifold 2 with G gauge field U2. Claim is if I can find a manifold of one higher dimension to interpolate between them, and I can find a gauge field U to interpolate between them, such that U is flat everywhere, then I'm in business, and Z of M1 U1 is going to be the same as Z of M2 U2. Proof? Well, simply follows from the fact that omega D is closed, right? I think about integrating d omega over the bulk, and that collapses to the integral of omega over the boundary, which proves this. Okay. Now, another comment Actually, you can think of this as a kind of one simple case of this. Another comment is that if I have a manifold with a boundary, then things are not so simple. If M has a boundary, product of a delta in M of omega of U S is not gauge invariant. So that doesn't mean that our initial partition function that we wrote was not gauge invariant. Our initial partition function with the g's in it is always gauge invariant. It's just that when I have a manifold with a boundary, this product is going to depend on the g's on the boundary. And so one really has to work hard to calculate the sum over the g's on the boundary in that case. So the boundary we'll see in general is kind of non-trivial. So just working with this kind of bulk contribution, that's not enough. How do we see explicitly? How do we argue that this is not going to be gauge invariant? Well, suppose this was gauge invariant even in the presence of a boundary. That would mean that on every d simplex, this omega d of u would be gauge invariant. But every on an open ball, right? Every G gauge field is pure gauge. So that means that would mean that this omega is always equal to 1 on every simplex, which is clearly not true. So it has to be non-gauge invariant on manifolds with a boundary. So in practice, Z of mu on a manifold with a boundary will have some kind of bulk contribution. So this is very schematic, but morally true. Times Z boundary of u, and by itself, this is not gauge invariant, this is not gauge invariant, but the product is gauge invariant. And this is the anomaly inflow argument. So this kind of tells you that you have to have something non-trivial on the boundary, otherwise there is no way to match this non-gauge invariance of the bulk. All right. So let's just, I know I'm running out of time, but let's just finish with
1 minute.
one generalized minute. Okay, so let's just discuss the simplest example, which we already alluded to, which is in 2 + 1 dimensions with a group G equal to Z2. Remember, we had this cocycle WGHK equal to -1 to GHK. Okay, so if I have a Z2 gauge field, what is that? Well, that's just a Z2 variable on every link of my triangulation. Let me call that Z2 variable A. A01, A12, A02, and I'm going to write things additively now. So this is the this is the flatness condition, which really means that d A of 0, 1, 2 is equal to 0. So A I can now think as a one cochain with Z2 elements, and this tells me that A is flat, is closed as a cochain, and gauge transformations are going to be just Aij going to Aij plus lambda I minus lambda j, where these are also in Z2, so this is just going to be A plus d lambda. So then my up to gauge transformations, my flat background gauge field A is just an element of the first cohomology group of the manifold. And well, what is this omega? Right, I'm integrating over my manifold over every tetrahedron in my 3 manifold. I'm doing -1 to A01 times A12 times A23, right? This is my cocycle. But this is just -1 to A cup A cup A, where we're using the cup operator from ordinary simplicial cohomology. If you haven't seen cups are more like wedges, but for discrete things. So then our partition function z, let's go here. Well, let's go here. Our partition function z is just an integral of A cubed, of this A cup A over the entire manifold, -1 to the power of that. So z and of course, since this is closed, then okay, the cube of the A is also going to be so it's clear that this is going to be gauge invariant. All right, so what are some manifolds where this is non-zero? So first of all, kind of the manifolds that condensed matter physicists care about. Manifolds of the form S1 cross spatial manifold Y2. Is it going to give me something non-trivial? Right, I can kind of decompose my H1 into something that lives on S1, generator of H1 of S1, and something that lives on Y2. Let's call this, I don't know, beta, whatever beta is. Right, and I'll, the only kind of term that can potentially contribute is alpha cup beta squared. But problem is that integral of beta squared over any orientable manifold Y2 is is 0 mod 2. As long as Y2 is orientable, then I get 0. So the kind of manifolds that we care about, that I don't want to say we care about, that we are most used to in condensed matter physics, for those ones, the partition function is going to be 1. So what's a manifold where this is going to be non-trivial? Anyone? What's an orientable manifold for which this is going to be non-trivial? No, S1 cross torus is of this form. Sorry? RP3, right? The three-dimensional real projective plane. I need just like 30 seconds. RP3 the generator. RP3, first of all, is oriented or orientable. There is a Z2. H1 is generated by Z2, which is just kind of gives non-trivial on the non-trivial cycle of this. This is S3 mod Z2 has one non-trivial cycle. And if I take the generator of this alpha and I take alpha cubed integrated over RP3, I get 1. So the partition function on RP3 in the presence of this non-trivial background gauge field is -1. So that's the way to distinguish this phase. Now, to conclude, I very much recommend the paper by Levin and Gu from 2012 that discusses Hamiltonian realizations of this phase and discusses a field theory that lives on the edge of that can live on the edge of this phase and cancel the anomaly, and also describes a way to distinguish this phase in terms of the statistics of the flux defects. So let me stop here.
Questions?
Yes?
Even for some discrete gauge symmetry, because you say that such some torus something, the contribution is trivial, so you don't need to worry about some orbital twist sector stuff, right? If I understand it.
So what this means is if you want to promote A to a dynamical gauge field, it means that the partition function on any spatial manifold, no matter what genus it is going to be the same in the presence of this non-trivial cocycle and in the absence. So, which means that the ground state degeneracy on any Riemann surface sigma is just going to be 2 to the let me make sure that I get this right. Minus two to the G minus G plus. Okay, it's 4 on the torus, and then every time you add a 2G minus 2. Thank you. The higher I go in genus, the larger this should get. Torus has genus 1, so torus should have. Yeah, I think this is good. Or equivalent to 2 to the early number minus. Whatever. This is right. Right. So it's not going to distinguish. It's not going to. In terms of the ground state degeneracy, whether I have a cocycle or not, it's not going to distinguish. But if you think about the S and T matrices of the that is the statistics, the braiding statistics of the anyons, that distinguishes, depending on whether you have this cocycle or not.